See, the problem what happens is now, if you see in the whole course in chemistry, if you have been bit active, you will find in the whole course of chemistry, organic chemistry comes almost at the end. The reason being, it involves lot of knowledge from the physical chemistry. It involves a lot of knowledge from the inorganic chemistry. It's a juxtapose of all and everything what you have learned, not just in 11th and 12th, from since class 8th. Yes or no? All the basic things also which you have been studying are actually coming into use here. Boiling points and all that you have studied in class 9th and 10th. But if you forget that, this is the type of mistake we will do in future. So that's where I always say that when it comes to organic chemistry, it's very important to go somewhere where a teacher can remind you about your past. Things which you have done in your earlier classes, at least in class 11th, those concepts which you have studied in class 10th, how they are playing major role here. Yes, otherwise we'll always get confused, because sometime back only we studied that Ri bond is weakest. Then why this fellow has the highest boiling point? Isn't it a valid question? So we'll be beginning this alkyl halides and aryl halides. When it comes to this chapter, most of these reactions we have kind of seen already. Most of these reactions, as I said, in GOC itself, I have revised the whole of organic chemistry for you. Yes, few of it we have seen, few of these reactions we have seen even in the hydrocarbons. Yes, where alkanes are reacting to produce alkyl halides. Yes, aryl halides is just an extension where aromatic compounds are giving their halides. Yes, benzene is reacting and forming aryl halides. That is what is we have seen in the past. Let's do it in a more detailed manner, and that's the reason we can go now fast, because we have done it very much in detail in the past. But let's see, I will not miss any points. Wherever required, we'll have a detailed discussion. So let's not be haphazardous in our approach also. I hope I am audible and clear.
Yes, sir.
Perfect.
Yes, sir.
Okay, let's move. So all these are halogen derivatives. These halogen derivatives could be alkyl derivatives, alkyl halides, or alkenyl halides, or alkynyl halides. That means all these three are hydrocarbon halides. Yes. And this one is aryl halide. That means aromatic compound is connected to a fluorochlorobromoido, these type of substituents. Apart from that, alkyl halides could be singly substituted, doubly substituted, triply substituted, or tetra substituted. That's possible, isn't it? So monohalides, dihalides, trihalides, tetrahalides. Apart from that, monohalides could be, if you change the chain from primary to secondary to tertiary, yes, that halide group is connected at the terminal carbon, it will be a primary halide. At the 2-degree carbon, secondary carbon, it will be a secondary halide. And similarly, at the 3-degree carbon, what will that be? A tertiary halide. Based on that, these three names. Are we good? Let's quickly go through this classification. That is what is explained here. Yes, what are alkyl halides? Some examples are given, their general formulas are given, which is too simple for you, correct? If it is alkyl halides, it will be CnH2n plus 1 X. Yes. When it is dihalides, obviously one less hydrogen. In place of 2n plus 1, it will become 2n, because another halide group is going and substituting it. Yes, substitution reaction happens. Okay, dihalides could be also of two types. That also we saw in the last chapter, if you remember. Yes, vicinal dihalides and geminal dihalides. That also we saw. If they are on the neighboring carbons, we call them as vicinal dihalides. If they are on the same carbon, we call them as geminal dihalides. Correct? Trihalides, some examples are given. Similarly, tetrahalides, some examples are given. I think you can make a sense out of it. Yes? One of the most famous trihalides are, anybody? Chloroform, bromoform, iodoform. Yes or no? Yes, one of the most famous haloforms. I mean, trihalides are these fellows. Okay, fine. Tetrahalides, another most famous one is carbon tetrachloride. Similarly, if you substitute all the hydrogens, even in ethane, that will turn into perhaloethane. Yes? Understood? Perchloroethane or perbromoethane, like that also we can name it. Carbon tetrachloride, though we call it, but there is IUPAC name also, which is perchloromethane. Are we good? Per represents all the hydrogens have been substituted with the halide group. Good. Now, one by one, monohalides, how do we name them? That procedure is given. If they are connected at the primary carbon, how are they named? That you should know. Correct. Two ways of naming it. One is halomethane or methyl halides. Correct. This is the IUPAC name. This is the old way where you use halides. Correct. But the same way, using halides sometimes becomes difficult if you have secondary or tertiary. There are also some places it can use if you have less number of carbon. Correct. Like here we have isopropyl fellow connected to halide, so we can call it as isopropyl halide, but better way is 2-chloropropane or 2-bromopropane. Clear? Next is, we can also go for this type of situation. Easy to understand. Secondary butyl, or at second carbon it is connected, so 2-halobutane. Are we good? Or tertiary halides, tertiary alkyl halides. Make sense? Good. What will be the IUPAC name of this? Let's say all of them are carbon, carbon, CH3, CH3, CH3. What will be the IUPAC name? 1, 2, 3. 2-halo. 2-methyl.
2-halo.
Propane.
Propane.
Good. Very good. They can also show isomerism. How? Either it could be positional isomerism, change the position of halo group from primary to secondary to tertiary. Good. Or you change the chain itself. This was a primary chain, straight chain. Now you have an iso chain. Correct? Then you change it to secondary chain. Then you go to tertiary chain, so on and so forth. Are we good? Even they among themselves also could be isomers of each other. So 1 and 2 chain isomers of each other. A and B chain isomers of each other. A and C position isomers. Yes or no? Position of chlorine group is changing. A and D chain isomers, as well as the chlorine has moved from 1 degree to 3 degree carbon. So both chain as well as position isomers. B and C. B and C. How about B and C? Here also chain
isomers
as well as position isomers. Position of chlorine also changing. This is 1 degree carbon. Yes, but this one is 2 degree carbon. So from primary to secondary carbon, the chlorine substituent has moved. Yes or no? Correct? Makes sense? So on and so forth. B and D are position isomers, C and D are chain isomers. I hope you can make sense out of it. One most important thing which we have been seeing in the past also, the order of reactivity, which is always this. Yes or no? Iodides are the biggest, and hence the chlorine and iodine bond will be the weakest, hence most reactive. Yes or no? You can check their bond energy value also, least bond energy. That means it can be easily overcome. Yes, kilocalorie per mole. CBr more than that, CCl even more than that, and CF has the highest bond energy. That means most difficult to break bond. Nice? Understood? Same way, if you check the nature of alkyl groups, which has the highest reactivity, obviously tertiary fellow has the highest reactivity. Why? Because when they participate in a reaction, they lead to the formation of what will happen? This X minus will leave, because already there is too much of steric hindrance, and this fellow himself is in big size. So when X minus leaves, there will be a carbocation, tertiary carbocation created. Now this carbocation which comes out as product is already highly stable. Because of 9 alpha hydrogens around it, hyperconjugation is playing a huge role, isn't it? Because of its stability, it tends to go to that. Hence reactivity increases. Make sense? Yes? If the product is very, very stable, the reactant will quickly react to give the product. That means the reactivity of the reactant will be very high. Simple? That's a simple logic here. Fine. Now we move on to the alkyl halides general preparation. Now, in the above type of situations, we have already seen this. In which type of mechanisms we have seen this thing happening? Which type of mechanism? Nucleophilic substitution reactions. Yes or no? And this one where tertiary alkyl halide is involved, is it SN1 or SN2? Is it SN1, SN2? It is SN1.
SN1.
Correct? Yes, there is only one molecule which is involved in the rate determining step, which is the slowest step. On his own, because of the steric repulsion, X minus leaves. Not that a nucleophile has to attack from the back side and then cause him to leave. That happens in case of primary alkyl halides. I hope you remember. Good. SN1, SN2 are going to play major roles here. Let's start with the introduction is over. Now we are moving to the preparation part. How do we actually prepare, first of all, monohalides? We can start from where? Alkanes. One of the most basic reaction. What is the mechanism here? Free radical substitution reactions. Alkanes are paramaffinous. That means less affinity towards reactions. No simple nucleophiles or electrophiles can break CC bonds or actually CH bonds. They're quite strong, correct? So for that, we need UV light or sunlight, correct? And then only free radicals are generated. And those chlorine free radicals can substitute hydrogen from here. Yes? Got it? I hope you know the rest. I'm not going to that detail. This is a process of halogenation which is happening. Similarly, hydrohalogenation also can happen. I hope it is clear. The process is same, isn't it? Now here, which type of addition is happening? Is it again free radical addition? Meenu? Which type of addition?
No, sir, not free radical.
Then?
Electrophilic.
Electrophilic addition, because what are we using? Unsaturated fellows. Heavy electron density, obviously electrophilic attack. Yes or no? Correct? Now if you have something like this, propene, where will H plus go? Markovnikov's rule will be followed. Yes or no? Yes or no? H plus will go to the terminal carbon. The carbocation will be created here at 2 degree carbon, which is more stable, and hence X minus will later on attack here and join, forming isopropyl halide. Yes, or 2-halopropane. Are we good? So we saw free radical addition. That's how we can kind of prepare alkyl halides. Free radical addition, substitution, free radical substitution of alkanes. We also saw electrophilic addition, hydrohalogenation of alkenes. From alcohols also we can produce hydrogen halides, provided we use some HX, some acid, HCl, HBr, like that, whatever we want to substitute OH with. At the same time, one reducing agent in the form of zinc chloride. Now, we can take only zinc also, but we wish to increase the concentration of X. So, we can go for zinc chloride, zinc bromide, all that. Are we good? Yes. What will it do? It will cause the X to be taken away by zinc. Then H plus will be attacking on the electron rich site. Are we clear? Which type of reaction is this happening? Who is he? Electrophile. Where is he attacking? At the high density site. So electrophilic addition happened. Then H2O is quite stable. So what will it do? It will leave. When it leaves, carbocation is produced. That carbocation again gets attacked by the nucleophile and it gets added there. Are we good? Yes. The whole reaction is clear.
Sir.
That's how we can get from alcohols alkyl halides. What does this zinc chloride do? Basically, it makes sure that there is no water present there. It is a dehydrating. It absorbs any type of water there, correct? This water which you saw there was quite unstable. So it absorbs that. That is where zinc chloride plays a major role, correct? So that the yield of the halide is highest. At the same time, it also generates H plus from the HCl. In the beginning, HCl was there. So Cl minus it took away. H plus is generated. Now that H plus is our electrophile, which get attacks on the lone pair of the oxygen. Correct? Fine. Again, concept is very simple. If your intermediate carbocation which is forming, which is this, if that fellow is more stable, that means this fellow will be more reactive. Simple. Is this clear? This is the concept which applies universally. Please understand. Let me mark it. This is a concept which applies universally in all the chemical reactions. If the intermediate carbocation which is forming is stable, that means reactivity will be high. Good. That's the reason we discussed previously that tertiary alkanes, tertiary alcohols, they are more reactive than secondary than primary. Are we good? This one was primary alcohol. But similarly, if you go for secondary and tertiary, they are much more reactive. Good. This reactivity order remains the same. No change here that you've seen already. Good. Are we clear? Then we move on to when it comes to HI. We know HI is highest in the reactivity among the hydrogen halides. Yes or no? It is so reactive that you don't even need zinc. HI has the highest reactivity. Yes. Readily reacts with either it is primary alcohol, secondary alcohol, or tertiary alcohol. Just bring them close by and alkyl iodide will form, water will be given off. Are we clear? Yes. Okay. But HCl, HBr still is at a boundary level, but HCl, they are all 1 degree, especially 1 degree alcohols, they're less reactive. Among these three, who is the least reactive? Primary alcohols. If you go for 1 degree alcohols, they're least reactive, and over that also, if you take HCl, all the more less reactive. That's where we need zinc chloride. Are we good? Yes. Sometimes acidified zinc chloride also. Some few drops of H2SO4 is also needed there to increase the reactivity. Are we good? Yes. One example is given here. We use zinc chloride, then you get your final substitution product. Yes. Nice. Let's move on. At normal conditions, without zinc chloride, if you try these two fellows to react with each other, no reaction. Straight and simple. In fact, these two fellows together, especially HCl and zinc chloride together, is called as Lucas reagent. And it participates in it creates a very beautiful test here. What is that? If you react it with alcohols, primary alcohol, secondary alcohol, and tertiary alcohol, you can identify primaries from secondary from tertiary alcohols using this Lucas reagent. How? When it comes to primary alcohol, very less reactive. We already saw that. 1 degree alcohols, correct? Degree is missing here. I hope you can make sense. So 1 degree alcohols are quite less reactive. Because they are less reactive, it takes almost half an hour time to actually form a precipitate, basically make the whole solution turbid. Yes, visibility of the solution goes away, the solution becomes turbid in almost 30 minutes. The same thing happens in case of 2 degree alcohol within a matter of 5 minutes. But in case of 3 degree alcohols, within a matter of a minute. Very fast. Yes, highest reactivity. Okay, phosphorus dihalide, we have already seen what type of test it gives, especially PCl5, test for OH group. Yes, alcohols also will give positive test. Why and how do you test it? The HCl fumes are given off. Is this clear? Whenever you take an alcohol, react with PCl5, it will produce RCl, phosphoryl chloride, and HCl fumes, toxic fumes will be given off, which you can test by bringing ammonia fumes close by. You will get a white fume of ammonium chloride. Yes or no? That's one way of testing it. Because we can test it, this is a proof for a group containing OH. So what we can call this? Test for OH group. Please write down somewhere. Test for whether a given organic compound contains OH or not, that we can test using PCl5. PCl3 bit difficult because you don't get any one here who has a very distinct way of identification or observation. That's where PCl3, not that powerful, but yes, PCl5 does that. PBr3, PI3, as the size increases, they are less stable, and that's the reason we don't go for them. Rather, what we can do, we can go for phosphorus plus Br2 or phosphorus plus I2 mixture if we want to get RBr or Ri. Are you getting my point? Yes. Here also for substitution, what are we doing? SN1 if primary alcohol is there. Yes. If tertiary alcohols are there. Are we good? Correct? Okay. Now we move on to the Darzan's process. Here SN1, SN2 both can undergo. If we use, rather than PCl5, what do we use? Thionyl chloride. Thio word comes why? Do you remember? In place of OH, what is present?
Thionyl chloride.
Huh. In
Thio is
place of
sulfur.
OH, if SH is present, what we used to call it? This is
Thio.
alcohol. This is thioalcohol. Yes or no? The word thio comes for sulfur, and when SOCl2 comes, we call it as thionyl chloride. This thionyl chloride also can give test for OH group. Why? Because once again HCl is produced, but bit difficult here because two gases are produced, not like the previous case. Are you getting my point? SO2 is also produced, which is a different colored gas. So not so foolproof test. That's why PCl5 is best, and that's the reason sometimes it is not included, and I will tend to remove it. Make sense? Yes. Again, if you talk about SOBr2 or SOI2, less stable. So what do we do? So actually, basically, we can't produce using thionyl bromide or using thionyl iodide, alkyl bromide or alkyl iodide. We can't use this process. Another very interesting way of preparation of alkyl halides is borodine-Hunn-Sticker reaction. Please remember this, mark it, very important. Why? Why is it important? It is specially known for increasing or decreasing, basically decreasing because forward reaction, decreasing the whole chain length by one carbon. It is known for that. Imagine you use silver acetate. Let's say you use silver acetate, react it with chlorine gas in the presence of carbon tetrachloride and heat it. You know what will happen? CO2 will be given off, and from silver acetate, if one carbon is gone, how many carbons remaining? Only CH3 is remaining. Yes or no? What will you get? CH3Cl, methyl chloride. Here you had acetate, that means ethanoate, and you're getting methyl chloride, not ethyl chloride. So the chain length has decreased by one carbon. Why? Because one of the carbon goes out, basically this fellow goes out as CO2, which is quite logical. We have seen this type of thing happening in the past. Yes or no? Yes or no? Silver combines with the chloride ion, and COO minus is there. It will give his lone pair back to the double bond, forming a double bond. Carbon will get a negative charge to take care of that. It will break and go out as CO2. And one of the reason why CO2 gas is getting off very fast is heating happening here. Yes or no? And not in water or not in any other type of solution. It is an organic carbon tetrachloride solution. So CO2 is bubbled out very fast. Are we clear? Silver chloride is heavy in nature. It will settle down. Yes, as a precipitate. I hope you remember what is the color of silver chloride, silver bromide, silver iodide from the inorganic chemistry portion. As we keep coming down, the color intensity increases. This is what? White in color, white precipitate.
White. Yellow.
Cream and yellow. Color intensity is increasing. Yes or no?
Yes,
Yes.
sir.
Good. Halide exchange. Sometimes if you go for more reactive let's say some metal halide, potassium halide, sodium iodide, potassium iodide, they will tend to normal substitution reaction will happen. Yes or no? Correct? Displacement reaction, not substitution. Displacement reaction will happen. Yes, this is more reactive, so it will substitute either chloride or bromide, because In metal iodide is much more reactive. So simple displacement reaction, like a normal displacement reaction, which you have seen where in inorganic chemistry. Yes, this reaction is known as Conant-Finkelstein reaction. Another one is SWOT reaction. If you go for a heavy metal, use a heavy metal along with some fluoride. So like mercury fluoride. Yes, mercury fluoride. If you're using, what will happen? It will displace chlorine, and you will get ethyl halide. HgCl2 will be given off. Ri and Rf, they can be prepared by this method only. That's where this becomes very, very important, because we could use other above methods, but they are more taxing. This is much easier. If you have to get alkyl iodide or alkyl fluoride, this method alone plays a major role and fastest way of actually getting them, because simple displacement, na? Yes or no? Simple displacement is taking place. Okay, fine. By reaction of alkanes with sulfuryl chloride. Sulfonyl chloride, I hope you remember. Sorry, thionyl chloride, I hope you remember. SOCl2, correct? If it is SO2Cl2, it is called sulfuryl chloride, not thionyl chloride. No, don't get confused. Here, the whole sulfur name is coming because SO2 comes, na, sulfur dioxide. So SO2Cl2 becomes sulfuryl chloride. So please do not get confused in SO2Cl2. And let me show you once again. Thionyl chloride, SOCl2. Yes, clear? Let's move on. Now, how do you produce using this? Again, same type of reaction. Only thing is, here uh, we are going to use organic peroxide. That means free radical substitution is something which is going to happen. You will get alkyl halide. Apart from that, both the gases, as it was coming off in the thionyl chloride reaction, HCl and SO2, they come out. Good. I hope everything is clear so far. Fine. So
Yes,
this
sir.
is all about preparation of monoalkyl halides.